in research, it's really important to be able to reproduce your experiment and to track them. And so the fact that to start an experiment on AI Core, you need to create a commit that is your experiment. And so when you need to go back to what was your experiment like 3 months after that, then you can just look at the code and you know exactly what's run and in which condition. And that's a key element for research.
Hi everyone, welcome to Let's Talk Research, the official InstaDeep podcast where we dive into cutting-edge AI research and the stories behind it. My name is Bora Gilola, I'm a research scientist here at InstaDeep.
And I'm Massimo Bortone, I'm also a research scientist at InstaDeep. Today we are looking at how our in-house AI compute infrastructure is powering the research we are conducting in the company.
Exactly, and to explain to us how that all works, we've got two experts from our R&D and applied AI teams. We've got Adrien Pichard and Armand Picard. Welcome both.
Good to be here. Thank you.
Great to have you here, guys. So maybe before we go into the nitty-gritty of how AI compute works, let's start with you, Adrien. So how did you join InstaDeep?
Sure. So I joined InstaDeep in 2021 for an internship in the infrastructure department as an MLOps engineer. So the subject at the time was to build some software that orchestrates some workload across some infrastructure. And the goal was to deploy some piece of compute, some containers, connect them with each other, and so they can act as one distributed computing. And this on multiple softwares with multiple frameworks that eventually led to the product of AI Core.
Yeah, super interesting. And how about you, Armand? What's your kind of story behind your time at InstaDeep?
So I actually joined the same team as Adrien back in 2021 as an intern. And then in my studies, my interests shifted a bit towards distributed computing. And so after I joined InstaDeep full-time on the research team, working on scaling reinforcement learning on our infrastructure across many GPU, but also on TPU. And now I'm working more on the research team, trying to scale different research projects.
So in our last episode, we had Alex Latour, our head of research, talking to us about kind of all the research that we do at InstaDeep. And he kind of hinted at the fact that there's a lot of stuff that needs to happen behind the scenes for that to be possible, right? You have a whole stack from software all the way down to hardware. And I was just kind of wondering if you guys would mind sharing a little bit about how that comes to be, what are the moving pieces that need to fall into place, and so on and so forth. So maybe we'll start with you, Adrien.
Yeah. So at InstaDeep, we manage all of the stack from the metal itself of the servers directly all the way up to the actual software that we use to do some research that will eventually lead to some paper publication and so much more objectives.
So if we kind of, if we assume that an organization kind of owns the whole infrastructure, right, and has control over it all, what is the advantage that gives you in terms of being able to do the research and kind of scale these models and so on and so forth? What kind of, what does that bring that you can't have otherwise?
I think the main advantage is this full stack integration, that if the person that is writing the software to do research can directly talk to the person that's manage the infrastructure, it's a huge advantage for performance reason, obviously, because we can try to, if we want to narrow down an issue, for example, over the network or over a GPU that have some issue, then you can just directly talk to the people, and that makes it much easier to squeeze the performance out of the accelerators. And also in terms of maximizing the utilization of the cluster that you have, then if it's not just an instance on GCP and that you actually have people managing the infrastructure, that puts maybe a bit more pressure on you, but that make then the utilization of the hardware much higher.
So that's obviously a tighter integration than if we were to just deploy our models on like some cloud provider. And actually, as a researcher, I know that this is like, it's such a benefit to have people you can actually talk to that, you know, they're in your company you can address them quickly to solve issues on the cluster. And yeah, it's been a great experience, for example, to work on Kyber, which is our latest, biggest cluster yet. Do you want to maybe share a bit of details on how Kyber came to be? And
At first, I think we had our first on-premise infrastructure in 2018. It was a cluster in London. It evolved through the years. So at first it was just a few servers with a few CPU and GPU nodes to host some reinforcement learning and deep learning workloads. And eventually, as I said, it evolved. We got some V100, some A100, and it got bigger and bigger. But in 2023, we decided that we needed much more, and that's why Kyber happened. So compared to that, Kyber, it's 3 times what we used to have. And it's some much more recent hardware with some very recent technologies in terms of CPU, GPU, networking, storage, everything. It's cutting edge technology. So, yeah.
And it's all on premise, right? So it's all kind of owned by the company and operated by the company.
Exactly.
So that kind of, I guess, takes me to the next point, which is as a research scientist, right? For me, it's kind of magic. I just log on and the resources are there. But obviously setting this up, kind of building a cluster from the ground up is a massive challenge in itself, I presume. So if you kind of have a little bit of insight to share into how you went about planning what the cluster should look like, and then also just kind of getting it into place, that'd be super interesting.
Yeah. I think that it's important to know that Kyber come from existing infrastructure that we had. So we had a lot of experience with this infrastructure, and it's kind of special at InstaDeep that we are not just doing deep learning. So we don't just need GPU nodes. We have a lot actually of reinforcement learning in research and also for some product like DeepPCB. And so here the needs is not only on having GPU power, but also we need a lot of CPU nodes because there's a lot of simulation that needs to happen. And obviously we may want to implement some of the simulation on the GPU when possible, but it's not always possible. So you need a lot of CPU nodes, and you need then your CPU node to communicate with your GPU nodes. But at the same time, we also have some deep learning where we have a lot of GPU that needs to communicate to each other. So that's why when building Kyber, we kind of upgrade some of the component that we saw was the bottleneck on the previous infrastructure. And so, when designing, the choice were obviously the latest accelerators, but connecting them with an RDMA networks. So that means like a really fast networks where the GPU can directly talk to each other. So RDMA stands for Remote Direct Memory Access.
Mm-hmm.
And so we are using like the Rocky technology. And so what that means is that a GPU can directly write something into the memory of another one.
Mm-hmm.
And so when you're training some big model, that makes a huge difference when you want to scale to a huge number of accelerators. And so designing everything. So the design was done in winter 2023, I think. And the project Kyber was delivered winter 2024. So it actually took only 1 year. And I really mean only because this type of project can take usually like 3 years.
Mm-hmm.
So first designing the infrastructure, like kind of trying to find the right people to implement that infrastructure. When we got an idea of what we want to put inside the servers. And so we partnered with Dell for the hardware, with SCC for the implementation of that hardware in the data center. And for the data center, we are in the Equinix data center in Paris. And so it's really nice to have all these good partners to help you in this type of projects.
It's quite impressive that you managed to design all of this, and it's a really well-functioning system in like this short amount of time. Especially also, I think from like we talked in the previous episode about all the different research branches that the team is looking at. So finding a good compromise that can satisfy every team demands is like it's not just about GPUs. And,
Exactly. Yeah, the design is very heterogeneous. Like as Armand said, we don't have only GPU, we have only CPUs for the reinforcement learning teams.
Yeah. I mean, and kind of going beyond so once you have the planning done, right, now you've got the logistical challenge of actually setting this up, right? I can imagine that also came with its own kind of, let's say, roadblocks and kind of challenges along the road. But I don't know if you have any stories to share on that.
Yeah, we had a few challenges with the deliveries that just got like too early or too late, and we have to sync with partners and everything. So it's been a busy year, and but yeah, it came through, and so now we're happy to be able to use the cluster efficiently now.
So Kyber has been now running for about a year, I guess, more or less. You planned it, you implemented it in Paris in the data center, and I guess, is it a fixed product now, or will it keep evolving? What have you learned in this year, and how is it gonna develop in the next future?
Yeah, so the whole design of the data center has been, it was made to be extensible. Like we have about 30 racks today, and we can easily extend in the future. So if we have some new accelerators that we want to connect to the cluster and use on the platform, that's something that we thought about and is doable.
So even new accelerators like TPUs or something that isn't there yet?
Yeah, we don't have plans yet, but we're thinking about TPUs, B100, I don't know. Any kind of accelerators or maybe more CPU nodes, anything basically.
Exciting.
I think it's important that because we have the knowledge, we've been doing that like for 2 generations of our own cluster. It's kind of like if there is a new accelerator, we can easily just, we already have the knowledge and the partners, so we should be able to do it if there is anything new.
Yeah, and that flexibility surely is also super important because of the fact that we have a very broad research portfolio. So the needs might evolve over time, and kind of you never know what exactly you're going to need. So you kind of have to bake that flexibility in when you're designing the system, right?
Yeah. Actually, having the people and not only relying on something on the cloud is quite important, I think.
Mm-hmm.
Especially, as you said, depending on the project, maybe you would prefer maybe to have a different accelerator because, I don't know, if I have better software support or just it's more optimized for this, or maybe you want to use, I don't know, FPGA or stuff like that, then if you have an infra team, then they can manage that.
Yeah. And in terms of, so I heard you mention software support there, right? So obviously you now have the hardware, it's all in place, it's ready to use, but there is yet another challenge, which is actually getting the people to interact with the hardware, right? So on top of this, there has to be a software stack that you essentially use to manage the hardware. What's the solution that we've kind of ended up with there?
So we have the hardware, and on top of that, of course, the software. So as I said in the introduction, we've been working on a lot of software to do like the orchestration and the scheduling of small and huge workloads, and it eventually evolved a lot, and now we have the platform that is called AI Core, on which we start our AI training experiments, or I say training, but basically it can run any kind of software, whether it's data processing or basically anything. And the goal of this platform is just to be able to use the infrastructure without having to know like how it works, how you need to configure, how to manage your drivers, etc. You just put like, I need this much compute, this much GPU, and I want it to be started this way. And you feed that to the system, and within a few seconds or a few minutes, you have your workloads that is running on the cluster.
I think the one key element to AI Core is the fact that you just don't give access to someone to the server so that it can run its experiments. Because when you do that, it's kind of unpredictable what you end up with, and you don't get nice reproducibility of experiments. And in research, it's really important to be able to reproduce your experiment and to track them. And so the fact that to start an experiment on AI Core, you need to create a commit that is your experiment. And so when you need to go back to what was your experiment like 3 months after that, then you can just look at the code and you know exactly what's run and in which condition. And that's a key element for research.
Yeah. It got me a bit of time to get used to it, because at uni you just get access to these huge clusters and you can do whatever you want as long as somebody checks on you. But you have, it's really hard to keep track of what you actually done in your history. But with AI Core, it's super easy. Like, you look at your Git commit history. If you're really careful about separating code changes and experiments, it's really nice.
Yeah, and if you make it easy to run experiment, then you can more easily run a sweep over some hyperparameter to check, as opposed to if it's kind of hard to do just because you have to set up the machine, then you may not do it. If it's easy to do, then you just create this experiment, and that's kind of also maximize the usage of the cluster, and the researcher are happy with that. So.
Yeah. I mean, we were talking about this again with Alex in the previous episode, that it is just extremely easy for me to say sweep over 15 different parameters, right? And just check what configuration is going to work for the exact kind of experiment that I'm planning. And having essentially software that bakes in keeping track of those experiments is super, super valuable. It makes life a lot easier. And it's just, it's super easy to retrain the same model and kind of iterate from there.
Yeah.
On the resource efficiency as well, it's AI Core is quite powerful on that subject. We often have some very small experiment that fail fast, like in 10 minutes it fails, so you have to retry, tweak some stuff, change your code, debug, etc. So some very interactive work. And sometimes you have some much longer trainings that can last, I don't know, a week, a month, several months. And so AI Core supports that. And also on the scale size, you can just start an experiment with a single CPU core and 1 GB of memory, or you can count in thousands of CPUs or terabytes of memory, and that's fine.
So what actually goes behind the scenes in AI Core? When I submitted my Git commit and I want to launch a job, an experiment, what happens behind AI Core that I don't see, but you guys have produced?
Basically, we detect that a new commit, like the user wants to trigger an experiment. And so at that point, we trigger something that we call the workflow. So the experiment goes through some different stages before it actually runs. So we have the steps where we clone the code. So we fetch the code and the parameters associated with it. That's defined in the manifest. So it's the small file that describes how big the experiment should be and how it should be started. Then we have the building phase. So as I said previously, it's running on top of Kubernetes, and so we have to build a container image, push it to some registry, and finally we have the submitting step. The submitting step is simply applying this new Docker image into the cluster, and then finally the running stage, where the experiment is actually running using this much compute and connects maybe with some other containers to do some distributed computing.
I think it's really interesting. Like, the part of actually running is just not running one container; it's running many, and it's kind of integrates directly with the frameworks that you want to use. So we have different integration with JAX or PyTorch to kind of set up the correct environment variable that these frameworks expect to just do their own distributed setup. But we also have support for Ray, and that's where the more advanced user, that's what they use, because you can define some more heterogeneous compute. And so you may want to have like some GPU and some CPU, and you want then your code to target different type of nodes. So when AI Core is creating the Ray cluster for you, you can use it and pretty much do whatever you want.
Yeah, I think you touched like a really critical point, and I can personally speak about it because this kind of flexibility and sort of power that AI Core has in managing heterogeneous infrastructure was critical for like the MLIP and MLDFT projects. Quantum chemistry, most of the code isn't really optimized for GPU yet. Some parts are, other parts are not. So in the big experiments that we have launched in recently, we needed this kind of flexibility, and the support for Ray was excellent. It was super easy to set up and get it to work, and yeah, it's cool to have you guys on board.
Yeah, that's one of the strange, like, I think thanks to all of the variety of projects we have at InstaDeep, well, we needed something that can support everything. So that was the challenge. It was not just reinforcement learning or not just deep learning. It has to be like able to run some many CPUs environment or some many GPU trainings. So yeah.
I'm curious about like what's your day-to-day work. So for me as a researcher, I sit down, I think I will design experiment, maybe I code something new. What's your day-to-day job? Maybe I can start with you, Armand.
So yeah, on my side, I'm working with some research team on kind of optimizing their code, and so a team may reach out to my team and say, oh, we have this particular problem. It can be optimizing a custom part of the code, like implementing some custom kernel to target specific accelerators, or trying to scale the model. Like they have a proof of concept of something that is working, like they are able to train it on a single accelerator or maybe on multiple accelerator with some just data parallelism technique. And my work is mainly to try to scale the research, and actually like scaling is not an option today. It's kind of just what you need to scale to make things work. And so yeah, I'm gonna work at mostly within JAX to implement different parallelism, like FSDP, tensor parallelism, pipeline parallelism, to be able to scale the model to a size where it just doesn't fit into a single accelerator, or sometimes it may fit inside a single accelerator, but it would just be too slow to train. And so you want to take advantage of multiple accelerator or multiple nodes even when you really want to scale. And that's when the fact that I came from the infrastructure team is important, because scaling, you need to know how the hardware is connected together. So if you know how the cluster has been designed and how to take advantage on the locality of some nodes, you may want to do some type of parallelism within a node, and another type of parallelism within a rack, and across rack you may just want to do another type of parallelism. So really have to think about the model, but also the hardware it runs on, and the different metric, with the end goal of just optimizing and making the research happen fast.
I think you have one of the toughest jobs instantly, because you need to be really good at understanding the models, like the intricate mathematical modeling that goes in them, but also understand how the machines actually work on like a really bare metal level, and combine them too.
So yeah, I also rely on some people from the infrastructure team, and that's where we can collaborate together to sometimes optimize some issue that we may encounter.
Yeah, that's where our work is complementary. And on my end, I'm working on more of the AI Core side of in the stack. So it's mostly developing the product, adding some new features, whether it's some queuing stuff or some, I don't know, any kind of feature that can benefit the user. Also spending a lot of time with bare metal teams. So it's the team that actually manage the metal. So the servers that actually manage Kybers, that like manage the infrastructure. They're a very busy team. Thanks to them, we have a beautiful cluster. Yeah,
I think that's maybe an underappreciated thing, or maybe something that a lot of people don't know, that it's not just you turn on a computer and you let it run.
No.
Like you need to kind of keep an eye on it, and things happen that you need to intervene. I guess like
Exactly. Yeah, we have a lot of subjects with these teams. So it's managing the cluster, fixing some issues, some hardware issues. It happens, and to do that, we set up a lot of observability. So through monitoring and alerting. So we have a lot of software that we rely on to be able to find them quickly, to avoid detecting them in the middle of a run that could affect anybody.
Yeah, I mean, you'd surely require a huge amount of agility as well, right? Because there's thousands of jobs running through the cluster every week, and so once an issue does arise, because inevitably it does, you kind of need to be able to respond to it quite quickly, right?
Exactly. Yeah.
Any late night stories of waking up with a burning server or?
Yeah, it happens, like some alerting at night or late evening, and we need to find like what fails and find back the user that got affected with it, and explain like what happened, like some stuff failed, some GPU had an issue, and
I think like the hardest part is that the issue that you see is more the silent failure, like when you got a run that is, for example, like a bit slower than usual. And so it may just be an issue with the hardware. And when you work with larger jobs, you may just see that, you created a large job and it's slow. But it may just be slow just because one of the accelerators is slow and it's slowing down everything because every other accelerator is just waiting for this one to do its job. And so that's when you start to do like distributed debugging of trying to find out what's happening. And so you really need to be able to address this issue quickly because you may just spending a lot of time and GPU being just idle just because of one issue. So
yeah. I mean, it feels like there's a lot of kind of detective work that goes into it as well, right? Like exactly pinpointing where the issue is, just so that you can essentially get rid of the bottleneck. Do you have any kind of general strategies that you use? How would you approach something where kind of the job is running fine, but it just smells a little bit, let's say, right? Like there seems to be something going on there.
So I think it's just observability, being able to have most of the metrics everywhere. So there is some hardware metrics that you want to have, but there's also some metrics that you get from your codes, because what can slow down is also like the data loading. So if the data loading is slower on one node and that the GPU of this node is waiting for the data, then it's slow. So looking at a lot of dashboard and trying to see like what's happening and try to compare to previous run.
So to observe how the cluster is running on a day-to-day basis, do you build your own tool to do this, or do you rely on like third-party software? Or
we rely on some open source software like Prometheus or Grafana. It's the stack that we use to monitor our infrastructure.
So we've touched a lot on kind of how AI Core and Kyber work together, are kind of designed essentially for each other in a way. And also that you're extremely flexible with the sort of workloads that you can handle, right? Different types of jobs, et cetera, et cetera. And that's reflected in the company's work. But of course, you can also kind of have external work happening on Kyber. Is that right?
Yeah. So the software started as a lot of small softwares that were just running independently one another, and we merged them together, glued them, and built some UI and some other nice stuff on it to get AI Core. So now it's not only an internal product, it's a product that is ready to host clients in a way that the client bring its own cloud and we connect to it, and AI Core can then run the experiment just like we do internally.
Really, really cool.
And I think that's important to say that we also use it. We not only use AI Core for Kyber, we also use it on the cloud for some project, right?
Yeah.
Where does the name actually come from? Like
AI Core?
Because it's core with a CHOR, like in chore, I guess.
So it was a mix between, first AI, artificial intelligence, and core was a mix of core, CORE, like the the core of AI, and the H was something for chore, to avoid having to every time you build your software, you don't do the chores.
Yes, the software does it for you.
Exactly.
Yeah. Okay.
Fair enough. And then a kind of final point that I wanted to ask about is, so you're always kind of running these huge experiments. I had this during my PhD as well. So I did a lot of MD simulations. Again, you're running these massive jobs and they're very power hungry, right? So obviously all this work that we do does have an environmental impact, and we need to care about how we manage that. And we actually need to make sure that kind of all this work that we do is sustainable in the long run. Has there been any kind of thought, decision, design that's gone into making sure that the running of Kyber and our essentially infrastructure is as environmentally friendly as possible?
We had actually, when choosing our partner, that was really something we want to look at. And so also on the location of the cluster, because the environmental impact basically come from the input, that is just electricity, and the output, that is heat. And so you want the input to be as clean as possible. And the fact that our data center is in France make it use like green energy and with really low CO2 emission. And our partner is really into this and is certified with different ISO that relate to environmental friendliness. And on the output, they are also trying to use the energy generated by basically the heat generated by the servers, to use it like on some urban heat networks, and also to heat some other infrastructure, like for example the Olympic pool or stuff like that. So there's many stuff you can do with the output actually of the data center.
So actually the pool that was used for the Olympics. Mm-hmm. That's so cool.
Yeah, Sibora. So your research is keeping those swimmers warm.
Yeah. Okay, I will keep submitting jobs happily.
So yeah, the heat is reused, and the energy that comes in is guaranteed 100% renewable. So as Armand said, we have some ISOs and some LEED certificates so it's some certification about green energy and sustainability.
That's really, really interesting. So essentially, just to tie this all back together, right? So by building our own infrastructure and also the software that sits on top of it, we've essentially been able to put ourselves into a position where we have complete control over how we want to run our compute, right? We can make it environmentally friendly, we can make it flexible, we can make it really as easy for the user as possible. And behind it all are essentially you guys and the ops teams, right? So yeah, from both of us, I guess, as RSs, a massive thank you. And thank you so much for coming on the show today.
Yeah, thanks for having us.
And to our listeners who might like to learn a little bit more about AI Core and check it out further, there will be a link in the episode description.
And yeah, once again, thank you for listening in and listen to us talking about big computers and how they power AI research at InstaDeep. Next month, we will be talking about everything genomics with our team behind the nucleotide transformer family of models. So I hope to see you there. Bye-bye.
Bye, everyone.